Hello again, students. Today we are going to work with sets and set operations. So it's our very first lesson over sets, and today is just a lot of vocab, and it's a lot of just learning new symbols and how those work. So for this notes page, which is posted online, please basically just read through it. Okay? And then what I'm going to do today for the lesson is go off to the side and give you examples of things that were written down in that notes page. Alright, so starting off, a set is a collection whose members are specified by a list or a rule. Order does not matter. You'll see these listed usually a certain way, but technically the order does not matter in a set. Alright, so for example, if I write down that A is equal to, so we usually use a capital letter to denote a set, and then we use braces to go around the set. So I can list the rule first, alright? So first I'm going to do the rule. So I'm going to say X such that, and I'll use a colon for such that, or you could see a bar right here. But I'm just going to use a colon. So X such that X is a letter in the English alphabet. Alright, and that is a rule. Alright, so this is known as a rule. So X such that X is a letter in an English element. So then you can start thinking about, okay, well, what values could I have for X? Right? Those are going to be called elements. So an element is an item in a set. And if I wanted to list out all of my elements, I'd start off with A, then B, then C, and I could list out all 26 of them, which would be fine. Or the shortcut is you can use an ellipse, which means 3 dots, dot, 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 saying that this, we're going to continue in this pattern, comma, we're going to end with the elements X, Y, Z. Alright, so this is a list of a set. Here is the rule for the set. Here's the list of the elements in the set. Both of these are equal. Alright, so that's why I used A to represent both of them. These are the same set. And what I said before was that A, this lowercase a, the letter A, is an element of set A. Alright, so this lowercase is an element. The symbol means element. It actually looks a lot like an E, so that's helpful. And it's an element of set A. However, set A, obviously, is not an element of A. Alright, let's go ahead and move on. Let's make another set. So I'm going to define another set, and I'm going to say set B is equal to the elements A, B, and C. Alright, so now I have another set, and it's also using letters, but not all 26 letters. Alright, so this is going to be helpful for me to talk about subsets. So a set A is a subset of set B if every element in A is also in B. Alright, now I've reversed the order on this. Alright, because A is clearly the larger set, B is clearly the smaller set, so if we're going to have a subset, okay, the smaller set is going to be the subset. Alright, and because every element in B, so A, B, and C, that's in set A, it means that B is a subset of A. And this is my symbol for subset. Alright, but A is not a subset of B. Why? Well, because A has all of these other elements, so D, E, F, G, everything else, that's not a part of set B. Alright, so that's what it means to be a subset. Now there's another type of a subset, and that's called a proper subset. So notice how this subset has a bar underneath it. Okay, you can kind of think of that as an or equals to. So this is saying that B has every element of A, could have fewer, or it could have every element of A. If it's a proper subset, okay, then the subset is going to be smaller than the set that it's a subset of. Alright, so A, B, C, there are only 3 elements here. Here there were 26 elements. It's obviously smaller. So not only is B a subset of A, but B is a proper subset of A. And what that means is I'm not going to put the or equals to, because clearly these two sets are not equivalent, because this one only had 3 elements and this one had 26. Now, obviously, A, if it wasn't a subset of A, it cannot be a proper subset of A either. All right, let's do another example. So let's go ahead and put another set in here. So let's define set C as C. Let's do A and then BC again. All right, so I could have switched that order around. I could have done CAB or BCA. The order doesn't matter. All right, but clearly I used the exact same elements in C that I did for A. Not A, I'm sorry. The elements in C as I did for B. So what this means is that set B is equal to set C. They're the same size, they have the exact same elements. Okay. We can still have these as subsets. So B can be a subset of C. Why? Because of this or equals to. Right here. Okay, so it is a subset of C. Likewise, C is a subset of B. However, because they are of the same size, and proper subset means that you have one that's smaller, B is not a subset, a proper subset of C, and B, well, I just did that one, and C is not a proper subset of B. Okay. All right, let's move on and talk about the number of subsets. All right, so in the notes it says a set of n distinct elements has 2 to the nth subsets. All right, so let's go ahead and use set C right here. All right, so C has 3 elements. So 2 to the n, well, 2 to the third, since it has 3 elements, that means that this set right here, ABC, has 8 subsets. Let's go through and let's start looking at those. So what I could do is I could just look at one element at a time. So A would just be a subset. And a set with just B in it would be a subset, and a set with just C in it would also be a subset. We could do 2 at a time. We could do A and B. We could do A and C, or we could do B and C. All right, so notice this element, or this set has 1 element, 1 element, 1 element, 2 elements, 2 elements, 2 elements. Our original set has 3 elements. So these are subsets. Not only are they subsets, but these are proper subsets. Why? Because these sets have fewer elements than the original did. These are not equivalent to this one. All right, so remember that that's going to be denoted with this. All right, so this is a proper subset of this. Technically, you could also say it's just a regular subset as well, or equal to. Just ignore the equal to part, okay? And it is a subset. All right, so that's 6. We have 2 more to go. So another subset would be if we have all 3 elements. So that would be A, B, and C. All right, so a subset can be equal to the original set, and in this case it is. All right, so this one is just a subset. It's not a proper subset because it has the same number of elements. It has the exact same elements. So it's not a proper subset. This is just a subset, and the way that we denote that is that same little C letter, but then it has the or equal to underneath, because in this case it is equal to. That's 7. We have 1 to go. And the very last subset that you have is going to be a set without any elements in it. All right, and that is what's called the empty set. There's a little bit more about that on your notes, but that's called the empty set. You can either write it as braces with nothing in it, or you can also write it with this symbol. It looks like a 0 with a slash through it. And that gets us all 8. All right, so the empty set is a subset of any set. All right, let's move on. Union and intersections. All right, so union and intersection. First, let's look at this. So the union, use this right here, this symbol. It actually looks like a U. It's going to be any element in A. So if I look at this Venn diagram, any element in A. So what I'm going to do is I'm going to shade this entire circle. Or in B. So set B, I'm going to shade the entire circle for B. And notice that when I did it, the overlap is also shaded. All right, so if I add another set, if I make it set A, B, and C, the union of all of them means anything and any part of any of these circles. All right, that's the union. It's not very exclusive, right? It's going to include basically everybody. All right, but the intersection, where it's closed, it's a closed off group. It's going to just consist of the elements in both A and B. So here's A, here's B, here's the only part where they overlap. If we extend that to A, B, and C, here is the only part where they overlap. All right, so you can see that union, you'd have more elements normally than you would with intersection. The intersection is going to be more exclusive. It's going to be only looking for the overlap. All right, so let's go ahead and do an example. All right, so first thing I'm going to do is I'm going to say U, which, by the way, represents the universal. So that means any possible element that we are working with. So I'm going to say our universal set are the numbers 0, 1, 2, 3, 4, and 5. And the way that you represent the universal set on a Venn diagram is it's the box that goes around your Venn diagram. All right, so that's why this actually has a U here, is it represents the universal set. So anything in the Venn diagram is in the universal set, and also there are going to possibly be elements on the outside. All right, so our universal set, we're going to pretend like nothing else in the world exists besides the numbers 0, 1, 2, 3, 4, and 5. And then I'm going to come up with another set, and I'm going to call it set P, and here's my rule. X such that X is a prime number. Now, I already said the only numbers we're considering are 0, 1, 2, 3, 4, 5, so if I wanted to list these off, I would only list off the prime numbers that are going to be smaller than 5. So your smallest prime number is 2. It's the only even prime number there is. Because remember, to be prime, it means that you have a number that is divisible by only itself and the number 1. All right, so 1 is only divisible by 1. All right, but 2 is divisible by 2. 2 is also divisible by 1. 3 is also a prime number. 5 is also a prime number. 7 is also a prime number. Notice that every other prime number other than 2 is going to be odd. All right, if I put the next odd number, though, that's 9, but 9 is divisible by 3 and 1 and 9 itself. All right, so this is our list. We are finished. It's going to be the numbers 2, 3, 5, and 7. But we weren't doing 7. Never mind. Sorry, I forgot. I defined my universal set to be through 5. Oops, so there we go. There's our set of prime numbers, so 2, 3, and 5. All right, let's go ahead and say that E is going to be X such that X is an even number. All right, and remember we can only go up to 5. So your even numbers, 0 is actually included as being even because it's divisible by 2. 2 is even, and 4 is even. All right, now, also in your vocab, it talks about complements. All right, so I can denote a complement with a P, and then right here, this little apostrophe. This is pronounced P naught, or the complement of P. All I need to do is I need to look at what values, what elements do I have in my universal set, what do I have in my other set, so in this case set P, and then the complement of it is going to be anything that is not in P, but it is in U. All right, so 2's in P, 3's in P, and 5's in P. So those are not going to be in the complement of P. But anything that isn't one of those will be. So 0 is in the universal set, but it's not in P. 1 is in the universal set, but it's not in P. 2's in P, 3's in P, but 4 is not in P. So there would be the complement of P. If we want to do the complement of E, same thing, only comparing to E. So 0 is in E, 1 is not, 2 is in E, 3 is not, 4 is in E, 5 is not. All right, now let's start using some operations. So let's start doing some unions and intersections. So if I do the union of P with E, so P or E, P union E, that means I'm going to list anything that's in P, so 2, 3, 5, and anything that's in E, and then also anything that's in both. So if there's overlap, I'm just going to include it once. So I'm going to write this in ascending order. I'm going to look at it just a little bit. My smallest value in either of them is 0. Then I have 2. It's in both, but I'm going to write it once. And then I have 3, 4, and 5. All right, so if I wanted to, I could do the complement of the union of P and E. And the only value that I'd be missing, the only element I'm missing, would be 1. All right, now let's do the intersection. So P and E has to be in both. All right, so what is the element that is in both? There's only one, and that's 2. Okay, let's do a few more. Let's do P and not P. All right, so here's not P, here's P. What's in both? Well, nothing. There's nothing that's in both at the same time, which means I can either write this as a set of braces with nothing in them, or I can write this as the symbol for an empty set. Okay, there's nothing. There's no element in the intersection of P and P naught. But what if I flip that around? What if I do P or P naught? Well, or means it could be one and one, or the other, or both. All right, so here's P naught. The smallest value, the smallest element I see is 0. Then I see a 1. Then I see 2. Then I see 3, 4, and 5. So notice when I had the set and its complement, it was 0, 1, 2, 3, 4, 5. The set and its complement will always be equal to the universal set. All right, so let's go ahead and one last thing with this example. Let's go ahead and show it as a Venn diagram. So my universal set is the box, and then I have 2 sets in it. I don't have to do the complements because that'll be taken care of for where I place my elements. All right, so this is my universal set. This will be set P, and this will be set E. All right, placing my elements. I have 1, 2, 3, 4, 5, 6 elements to place. 0 is in set E, so I'll put 0 in the Venn diagram for E only, not in the overlap because it can't be in circle P at all. 1 isn't in either, so it's going to go outside of the circles, just in the box, the universal set. 2 is in both, so it needs to go in the overlap. 3 is in P only. 4 is in E only, and 5 is in P only. All right, so that's going to be day 1 with working with sets and set operations. There is one last topic that got thrown in with vocab, so let's go ahead and look at one example for that. And this is going to be what are called Cartesian products. All right, so Cartesian products, let's go ahead and define 2 sets. So I'll let C represent an outcome of a coin toss. So think of a fair coin. You can either get heads or you can get tails. So 2 elements there. Let's let D represent the outcome of rolling a fair die, 6-sided die. So that would be your numbers 1, 2, 3, 4, 5, or 6. So why the Cartesian product is going to be helpful, all right, so this is how it's denoted, C by D, is it gets you ordered pairs. So it's going to be the list of all of the ordered pairs with this element paired with everything from the other set. All right, so what I would do is I would take H and I'd pair it with 1. Then I'd take H and I'd pair it with 2. And then I'd take H and pair it with 3, H paired with 4, H paired with 5, and H paired with 6. Now I move on to the next element in set C and do the same thing, pair it with every element in D. So that would be T1, tails paired with 2, T3, T4, T5, and T6. Now, I could switch that order around. I could do D by C, and then that just means that all of these coordinates would have their ordered pair switched around. So instead of having H comma 1, I would have 1 comma H, and then 2 comma H, and so on. All right, so that means that once the order is switched, that these Cartesian products are not commutative. All right, now, the reason why Cartesian products are going to be helpful is eventually when we get into probability, which I kind of gave you an example of that right here, is once we start figuring out, okay, if we flip a coin and then roll a die, what are going to be our possible outcomes? Well, this Cartesian product represents all of our possible outcomes. Flip that order around, let's say we roll a die, then flip a coin, then this Cartesian product would represent our total, our number of elements, our total possibilities of all of our outcomes. And that's going to be very important when we're discussing probability. All right, so a lot of new vocab today. Please become familiar with it, memorize it, and memorize those symbols.